Today's lecture is going to be about integral equations and your very first introduction to an integral equation. Okay, so we'll keep it very simple to give you an idea of what exactly is an integral equation and how is it different from any other kind of equation you have seen so far. Okay. Right. So, in order to look at this, there are what I will do is we won't even go into electrodynamics. We will just take a statics case. The equation for which a class 9 student can tell you, okay, potential due to a charge, that kind of a thing, and then we will solve it. Okay. So, let us look at a line charge problem. Okay. So, what do I mean by a line charge is, let us say that I have x, this is my axis, and over here I have put a conductor. Okay, it's a conductor and diameter over here is say some 2a. Okay, imagine it's like a thin wire basically that I have placed along the y axis, and it's a statics problem. So, there are no fields that are varying in time, and what I have done is I have connected this whole thing to a constant voltage. Okay, so let us make that simple. Let us even just make it 1 volt. Okay. So, this wire which is lying along the y axis, it has some length L, it has 1 volt. Okay. You will make it even simpler, perfect conductor. Okay. Now, if I ask you what is, let us say, the voltage at some point over here, V of R, there are charges everywhere, right. Now, even though this wire has a surface, right, it's a realistic object, it's a wire, it has some surface area, but we can simplify our problem because there is nothing else around, all the charge will be uniformly and symmetrically distributed about the circumference. Okay. So, instead of dealing with a surface, we can make life simple and just deal with a line. Okay. If you want to get the correct surface, get the correct charge, you have to multiply by the circumference or whatever. So, we will deal with a line charge. Now, if I ask you what is the potential at this point over here, what law would you use? Yes, coming from Gauss's law, right. Sum the contribution from every small point over here. So, this equation that I have written here, this gives you the voltage at a point R. Because I have lots of small charges along this entire length over here, it will not be a summation, it will be a integral, right. So, what is rho over here? What would you call it? Line charge density, right. Okay. So, rho integral dl, and I have in the denominator should be what physically? Distance between the charge and the point, right. That is what gives me the total potential. Total potential is the integral of all the potentials due to every one of these fellows, and this capital R that I have written over here is simply the Euclidean distance. Okay. So, the x, y and z, these are the observer points, right, and the prime coordinates correspond to what? The source points, right. So, those are also the limits of, the variable of integration, right. So, those refer to the points along the wire where the charges are, right. So, the prime coordinates are the source points, okay, and this over here is the observer point. Okay. Now, so now you can sort of appreciate the problem. This observer standing over here wants to find out the potential. In order to find the potential, we have come to this expression over here, which gives me the potential as a function of all the other variables. So, what is the problem? What do I know? What do I not know? Do I know rho as a function of r prime? As a function of the length along the wire, do I know the charge density? If I knew it, the problem would be done. Then I just have to evaluate this integral and I will get V. But do I actually know the charge distribution? I do not know, right. I gave you a wire, all I told you was that it is connected to a constant voltage source. So, the voltage along the wire is 1 volt. But now how will the charges distribute themselves? If I put, will the charges, for example, will rho be constant as a function of r prime? Is that physically meaningful? Imagine you have, let's say, 10 charges. I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 charges, and I leave them. Will they stay like that? Where will they go? They'll move according to each other, but intuitively, what kind of distribution do you expect? They'll move away from each other. They're all like charges. They will move away. Till what point can they go?
Until equilibrium comes.
Until equilibrium, right? So they will they be clumped up towards the center or towards the ends? We would expect towards the ends, because on the end points there is no force from the other side, right? And we are assuming that the situation is not so dramatic that the charge jumps off the thing, right? So the charges sort of will accumulate there. So rho actually we don't know. If we knew rho, then this problem was simple. I will calculate this integral numerically or analytically depending on the situation, and I will get voltage. So before we even get into solving something and get lost in the details, we should appreciate what is known, what is not known, right? So first of all, I need to find rho as a function of space. Once I find rho, the problem is simple. I will just plug it into this equation and find the voltage. Okay, you will find this general principle applied in almost all integral equations. There will be some intermediate variable which I don't actually care so much about. I mean, this observer over here just wants to know potential. He or she is not interested in what is the line charge density, right? So, but you have to solve for one intermediate variable before you solve the actual voltage. So that's the strategy. Right. So what is unknown over here is rho, and what is known, this constant thing over here, constant voltage. This is what I've given you. Do we have enough to solve this problem? It seems like, I mean, think of a wire. I connect it to a 1 volt source. In principle, that should be all, right? But looking at these equations, it seems a little confusing. How will we find this? So we need to somehow arrive at a system of equations which captures all the information that is given to me. Okay. So what is given to me primarily is the fact that voltage is constant 1 volt. Where all is the voltage 1 volt? Where is it? Where is it known to be 1 volt? In space, where all is it known to be 1 volt?
Y equal to 0 and y equal to L.
Y equal to 0 and y equal to L. Why? What about in between?
It's
It's equipotential. So everywhere, if I pick any point on the wire, voltage will be 1 volt, right? So in this equation over here, if I take this equation, this capital R over here is a function of, I mean, this is actually written like this, right? Right, it's the distance between the source and observer point. There is no choice on the source point. Source point is fixed, it's along the line charge. So I have 1 degree of freedom over here in specifying where should I choose my R, my observer point. So I won't be greedy. I actually want the potential at this point over here away from the wire, but let's not be so greedy. Let's not fix R to be this point, because then I don't know rho. How will I solve this equation? So what we can do is we can choose this R to be at a point where I know the voltage. So if I choose this R to be along the y axis, so how will I characterize any of these points? What will be the x, y, z coordinates of of a point that goes along the y axis? 0, y, 0, right? For different y, and y is going to vary from 0 to L, right? So this is my R. Okay. For these points, I know the potential, right? So the left hand side of this equation, what does it become? This equation over here. What is the left hand side of it for these points? 1. I know it, it's 1 volt, right? So I will write 1 is equal to 1 by 4 pi epsilon naught, right, integral over L, and rho of, so let's just let's make this R prime, right, dy prime Okay. All others, I mean x and y are 0, x prime y prime also we can ignore it for now. Okay. So, it is function of these two variables. So, notice another nice thing that happened by choosing r to be this way. This denominator, will it ever go to 0? No, right, because I have said the sources are on the surface of the conductor and my the r that I have chosen is on the axis of the conductor, right. So, there is the minimum distance between these 2 points is how much? A, in this case A, right. So, this r y prime equal to 0 never happens, and we need that because we are actually dividing by 1 by r, right. So, we have come to an equation where nothing bad is happening, there is no singularity, nothing is blowing up. Okay. So,
we are taking the charges are accumulating on A.
On the surface, because we expect charges will go and flow to the surface, they will not.
We are not approximating it to just a line.
No, we are approximating the charges to be A on the surface. In a realistic situation, they will be smeared all over the surface of the conductor, right, but they will be symmetrically distributed. So, instead of dealing with a 2-dimensional surface distribution, why not I deal with just a line charge, and once I get that, I know that I have to just normalize it to get the correct surface thing, because it is the same thing that will be repeated at every theta. Okay. So, just to make our calculation simple, let us pretend that the charges are on one line, just to keep it simple, on the surface, on the surface. Okay. So, these kind of convenient assumptions you will find made throughout electromagnetics, otherwise unnecessarily you will be solving a 2 or 3 dimensional equation when actually the actual physics is only 1 dimensional. Okay. And we can make this assumption because this current, I mean this wire is lying in free space. So, the charges will be symmetrically distributed as a function of theta, right. So, that is what we will deal with. Okay. So, what you have seen now is your very first integral equation. Okay. Now, why do we call it an integral equation? If you look at your equation over here once more, the unknown, in this case the unknown is rho. The unknown is sitting inside an integral sign, that is why it is called a integral equation. Okay. So, this is just one example of many types of integral equations. So, we will just make a small detour to types of integral equations, right. So, we will start from the top. So, what we just saw was a Fredholm integral equation. This is of the first kind. Okay. So, this k over here is called a kernel. Okay. This psi over here is the unknown. Okay. When the limits of integration are fixed, right. So, that gives us a Fredholm integral equation. Then you also have a Fredholm integral equation of the second kind. What is the difference? The unknown is both inside the integral sign and outside, right. Psi is inside and outside, right. So, in and out, and this is only in. Okay. Later on in the course, we will come across both, I mean we have already seen the first one and we will later in the course come across the second one also. Okay. So, it is not, I mean these will be used very soon. Further, you notice the second equation has one more parameter that has come upon, which is this guy lambda. Okay. So, lambda is also unknown. You can think of this as the equivalent of a eigenvalue problem. When you write a eigenvalue problem, what do you write? You write Ax is equal to lambda x, and when you write this equation, you do not know x and you do not know lambda. You solve for both one by one, right. So, we have encountered such equations where there are two unknowns. So, this is a generalization of that, where this lambda parameter is also unknown. You can think of it as an eigenvalue. So, these two are Fredholm integral equations, and electrical engineering comes across these many times. Okay. There is yet another kind of integral equation which we will not come across in this course, but they also occur throughout engineering and even economics. It's called a Volterra integral equation, which is almost identical to a Fredholm integral equation. Can you spot the difference?
Limit is variable.
One of the limits of integration is a variable, right? So, I have x over here, x over here. Everything else is same. Okay. So, these are the two kinds of integral equations that you will come across in the engineering literature, right. This f over here had better be known, otherwise you can't solve the problem. Okay. This f may be 0 or it will be, or it can be non-zero. If it is 0, standard terminology, we will call it a homogeneous equation, and else I call it a non-homogeneous. Okay. So, when I look at, let us say, the equation that we had on the previous page, right. So, I had V of r is equal to 1 by 4 pi epsilon integral of rho r prime d y prime r of y prime and in 0 to L. This was our integral equation. So, from these 4 equations that we have on the board, which of these does it look like? Looks like a, okay. So, the complete, what is the complete description of this integral equation? So, first of all, Fredholm, why not Volterra? Limits are known and fixed, right. So, it is a Fredholm integral equation, IE, of which kind? Which kind? First kind, right. There is the unknown is appearing only inside the integral sign. In the second one, it is also outside, right. So, of first kind. And is it homogeneous or non-homogeneous? It is non-homogeneous. Why? Because what is fx over here? V, the potential, right. So, it is non-homogeneous. What is my psi in this case? If I want to draw a one-to-one analogy between this guy and this guy, what is my psi? Rho. What is my kernel k? 1 by r. What else do I have? F, right. So, f is V. So, that completes the full description of your integral equation. So, you need to specify all 3, Fredholm or Volterra, first kind or second kind, homogeneous or non-homogeneous, then your integral equation is fully specified. Okay. These integrals have been written as an integral in 1 dimension, but as we go further, these can be integrals in 2 dimensions, 3 dimensions. The terminology will be the same. Okay.